In this section, we'll look at how we can use the equilibrium constant to tell whether a reaction is at equilibrium by comparing it to the reaction quotient. So suppose we have the following reaction, and the concentrations of N2H2 and NH3 in the mixture are 1 molar, 6 molar, and 3.96 molar, respectively. And they give us the chemical equation for the Haber process. So again, taking nitrogen, combining it with hydrogen to give us ammonia. So suppose we want to know if this mixture is at equilibrium. And if it's not at equilibrium, which way should it shift in order to reach equilibrium? And they also give us a Kc value, and they tell us what temperature we're at. So how can we figure out whether this is at equilibrium and which way it should shift? To do this, we'll look at the reaction quotient. So this is the number obtained by substituting the reactant and product concentrations, or the partial pressures, at any point during the reaction into an equilibrium constant expression. So basically, it's the exact same thing as calculating the equilibrium constant, but it's at any point during the reaction. So in other words, we might not necessarily be at equilibrium, and this is one way we can find out, but you calculate it the exact same way. It says if the system is at equilibrium, the quotient Q will equal the equilibrium constant. So if we are at equilibrium, the reaction quotient will be equal to the equilibrium constant. And if it's not, we'll take a look at how to decide which way to shift. But notice it's calculated the exact same way, so products over reactants. So calculate the exact same way as the equilibrium constant. So if I asked you, for instance, to write a reaction quotient, you would write the exact same thing as if I asked you to write an equilibrium constant. The difference is we may or may not be at equilibrium. Okay, so we have our same reaction. It says for this reaction, and they give us the concentrations, and they ask us to calculate the reaction quotient. Okay, so we have 1 molar, 6 molar, and 3.96 molar again. So we'll set up our reaction quotient. So again, products, okay, so our products over our reactants, just like always. Okay, remember that you need to bring down your coefficients as the powers. Okay, so now all we have to do is sub in what they gave us for concentrations. Okay, so I'll just go through this quickly. And we end up with a reaction quotient, so Q. So is this at equilibrium? No. Why? Because the equilibrium constant and the reaction quotient are not equal. So this tells me that no, this reaction is not equilibrium at this point. So what direction should it shift if I want to reach equilibrium? So here we'll compare and look at what it means for the Q value to be less than or greater than Kc. So I just made a reminder here that Q, again, is the products over the reactants. And let's take a look at what this can mean. So here we have Q, which is less than Kc. So what does this mean? So if Q were equal to Kc, so let me go back one. If Q was equal to Kc, we know we're at equilibrium. So this would mean, well, we know we're at equilibrium if Q is equal to Kc. So what if Q is less than Kc? So remember, it's products over reactants. Okay, so if Q is less than Kc, if the value is less than we want it to be, that means what? That means that the reactants are too high as compared to the products. In other words, our numerator is not big enough compared to the denominator that we have. We want to make this number larger. So how can we do that? We can shrink our denominator and raise our numerator. In other words, we need to shift towards the products. So we want to make our products bigger compared to our reactants. Okay, so we need to shift towards our products to make our numerator bigger than our denominator. Or at least just make that ratio larger. It doesn't have to be larger then. Just to make the ratio closer to what we want. So we'll shift towards products. And that will move us back towards equilibrium. So what if our Q is too high? So if Q is too high, that means we have more products than we need as compared to our reactants. So our numerator is bigger, or too much bigger than our denominator. Okay, so in this particular case, we want to lower our products, raise our reactants. Okay, so that means we need to shift towards our reactant side. Okay, so if we have Q less than Kc, shift towards products. Q greater than Kc, shift towards reactants. Okay, so movement toward equilibrium changes the value of Qc until it equals Kc. But the value of Kc does not change. So the equilibrium constant is not changing. We're just changing our reaction quotient, which can be measured at any point during the reaction, until it equals Kc. Okay, and again, if it's too low, so Q less than K, shift towards product. Q greater than K, shift towards reactants. Okay, so here we say the brown gas, we have a problem to try. Brown gas, NO2, can form the colorless gas N2O4 as seen in the following equilibrium. The Kc value is 171 at 298 K. And here we say 2NO2 gives us N2O4. And it says suppose the concentration of NO2 is 0.015 molar and the concentration of N2O4 is 0.025 molar. Wants to know, is Q larger than, smaller than, or equal to Kc? Okay, so give it a try. See if you can calculate Q real quick and see whether it's larger or equal to the K, or smaller than or equal to Kc. Okay, so how do we calculate Q? Remember to calculate Q just like we calculate the equilibrium constant. So we set up our equilibrium expression, products over reactants. Here NO2 will be squared due to the coefficient. Then just plug in your numbers, and you end up with Q equal to 110. Okay, so is this larger than, smaller than, or equal to Kc? Of course, Q is smaller than K. Okay, and ask us a second question, is that if the system is non-equilibrium, in which direction must the reaction proceed to achieve equilibrium? Okay, so think about this one, see what you come up with. Okay, so we know, no, the reaction is not equilibrium because Q is not equal to Kc. And since we have Q smaller than K, it must shift towards the products to achieve equilibrium. Okay, so that's how we can use the equilibrium constant along with the reaction quotient to figure out if a reaction is equilibrium and which way it should shift. The last section in this chapter is the Châtelier's principle. And this one is mostly just theoretical. There's no real math involved with this section. Okay, so what exactly is the Châtelier's principle? So if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. So this tells us that if we apply a stressor in the form of temperature change, pressure change, or change in concentration to an equilibrium reaction, the reaction will shift basically to relieve that stress. Okay, so here we have two water reservoirs. So we have a thinner reservoir and a fatter reservoir. So we can kind of imagine some things here. So firstly, what would happen to the water level? So here they're even. And we'll assume that this reaction, or these two reservoirs, will always try to fight to keep the water level even. So what would happen then if we expanded this reservoir to be equal to the in size to the other? So now this water has a lot more room, so basically we've increased the volume. So what would happen to our left-hand side? Well, we would expect the water level to go down and this water level to go up to meet it. Okay, so we would expect water to flow in this direction. Okay, until we had some new water line maybe around in here. Okay, what would happen, for instance, if we were to, well, if we squeezed this one on the right a little bit, assuming that this one could hold enough water, again, we would assume water would flow this direction, increasing this water level until they were both the same. So maybe they were more like up here now. So the point is if we affect one side of the reaction. So if we do something to remove, add, remove a reactant, change the pressure, change the concentration, change the temperature, that will affect both sides of the reaction in order to relieve whatever stressor we've put on it. Okay, so let's look at the first one, temperature change. So generally speaking, if we have an endothermic or an exothermic reaction, we can write heat as either a product or as a reactant. So if we have an exothermic reaction, obviously heat is a product. If we have an endothermic reaction, heat is a reactant. So with this example, we have heat driving the forward reaction. So if we remove heat, so if we cool this system down, we may expect the equilibrium to lie in this direction, simply because there's not much heat around to drive the reaction forward. Okay, so we're removing a reactant by cooling it. So our equilibrium will shift back towards reactants. So likewise, if we add heat, so now we're adding a reactant. Okay, so we're adding a reactant, so we'll drive the forward reaction. So now we have too much reactants essentially, or too many reactants, and that will drive the forward reaction. Okay, so essentially just using temperature as a reactant or as a product. So you can think about that in terms of which way would it drive the reaction, just in terms of endothermic or exothermic. That's one way to think about it. Or you can think about it in terms of, are we adding a product or are we removing a product? Are we adding a reactant or are we removing a reactant? Okay, so in that way, temperature affects our equilibrium. So here we've kind of broken this out, just as what I was saying before. So here we have heat as a reactant. Okay, so if we remove heat, we're removing a reactant, so we'll shift in this direction. If we add heat, we're adding a reactant, so we'll shift in this direction. Okay, so that's one of the very basic principles of Le Chatelier's principle. Okay, so what about the effect of volume change? Okay, so here we have the Haber process again. By the way, if you're interested, you should look up the Haber process. This is a very important process that actually produces ammonia. This is how we produce fertilizers. There's also some other uses of it that I don't want to get into here, but it's kind of an interesting piece of history if you're interested. Okay, so here we have nitrogen and hydrogen give us ammonia. So what would happen if we change the volume? So suppose we increase the pressure. Well, the equilibrium reaction will always shift due to an increase in pressure towards the side with fewer number of moles of gas. So it says because there are more gas molecules on the reactant side of the reaction, when the pressure is increased, the position of the equilibrium shifts towards the side with fewer molecules to decrease the pressure. Okay, so if we increase the pressure of a reaction, it will shift towards the side of the reaction, the side of the equilibrium, with fewer moles of gas. So on the left-hand side we have 4 moles of gas, on the right-hand side we have 2 moles of gas. So increasing the pressure will shift this to the right. Decreasing the pressure does the opposite. So since we have 2 moles of gas on the right, only 4 moles of gas on the left, if we decrease the pressure, it will shift towards the side with greater number of moles. Okay, so here it gives us a note that says, the transformation of nitrogen and hydrogen to ammonia is of tremendous significance in agriculture, where ammonia-based fertilizers are of utmost importance. Okay, so again, that process that gives us ammonia for fertilizer is the Haber-Bosch process. Okay, and it happens to be exothermic. So if we combine nitrogen with hydrogen, it gives us ammonia and energy. Okay, so remember we have 4 moles of gas, 2 moles of gas, and we're also giving off heat. So this is an example of the system that might be used to produce ammonia through the Haber process. And they use a few components here, and I wouldn't ask you to recreate this, but I want to show you how some of these ideas are actually used in the real world to make reactions more efficient. So the first thing we see is that we have some reservoirs. So we have things like, and I'm just going to point out some of the parts of this first, and then we'll go through it. So first thing is we have our inlet for our reactants, so N2 and H2. So this is how we're feeding in the stream of our reactants, so the two gases. So they come in here, they flow down through the system, they come down here, and they start being pushed upwards towards the catalyst. So this catalyst will help the process along. Okay, and we pass over a heat exchanger. Okay, then we go through a valve. We continue being pushed this way, and we go through another heat exchanger, which turns the ammonia back into a liquid. Okay, and it drips down, and we go through a refrigerated coil, which makes this very cold, and we collect our ammonia, and the unused N2 and H2, because it's not quite cold enough to capture that, is reused through the stream. Okay, so that's the basic flow. Okay, so what's the point of this? What am I telling you this for? So the point of this is there's a couple things here that are using Le Chatelier's principle to drive this reaction forward. So the first one is increased pressure. So remember that we have 4 moles of gas on the left, only 2 moles of gas on the right. And we said that if we increase pressure, we'll shift the equilibrium to the side with fewer moles. Okay, so if we increase the pressure by increasing the pressure of our reactants, we'll drive this forward. Not only are we adding reactants, but we're also increasing the pressure. Second thing, we said this was an endothermic process. So that means if we start to remove heat, okay, here, and here, we'll also drive this forward because we're removing a product. So if we remove a product, we also drive the reaction forward. Last thing is we remove the ammonia, we turn it back into a liquid, or turn it into a liquid, with this refrigerated coil. So what does that do? Now we're removing our ammonia product. Okay, so in both ways we're removing ammonia and heat through cooling. We're driving the pressure by increasing the number of reactants, or by increasing the amount of the reactants. We're also driving the pressure up. Okay, so in all of these ways, and we're using a catalyst to help the reaction along. So in all of those ways, they're driving this reaction forward to get the most efficient process they can. Okay, so hopefully you find that interesting, because this is how these principles actually come into play in the real world. Okay, lastly, the effect of a catalyst on an equilibrium. So the effect of a catalyst on equilibrium, so we just showed that we use a catalyst in this situation. Let me go back. Does not like letting me stay on that slide. There we go. Okay. So the effect of a catalyst on equilibrium is just to lower the activation energy. Okay, so this will make the forward and reverse rates of the reaction quicker, or more efficient and faster. But what it doesn't do is it doesn't change our equilibrium concentrations. All it does is it makes a reaction reach equilibrium more quickly. Okay, but it doesn't actually change our Kc value. It doesn't change our equilibrium concentrations, nothing like that. It just makes our rates faster by lowering that activation energy. So in other words, a reaction will reach equilibrium more quickly, but the equilibrium will be exactly the same. Okay, so a couple of problems for us to try. So it says, will the number of moles of product increase, decrease, or remain the same when each of the following is subject to a decrease in pressure? In other words, an increase in volume. So we're decreasing the pressure, and it wants us to know which way it will shift. So will the moles of product increase, decrease, or remain the same? Okay, so we have PCl5 in equilibrium with PCl3 and Cl2. Okay, so if we decrease the pressure, in other words, will it shift right or left is kind of another way to think of it. In other words, will it increase or decrease or remain the same? So increase means we're shifting to the right, decrease means we're shifting to the left. So remember, it's always going to shift towards the side with more moles if we decrease the pressure. Okay, so the first one we have 1 mole versus 2 moles, so of course we'll increase the amount of products. This one we have calcium oxide solid plus CO2 gas, giving us calcium carbonate solid. So we'll increase or decrease the amount of product. So of course this one would decrease, in other words, shift towards the reactants. Okay, this one, so we have iron plus H2O, which is gaseous, giving us solid iron oxide and hydrogen gas. Okay, so if we decrease the pressure, which way will this shift? So we have to look at the moles of gas. So on the left-hand side, we have 4 moles of H2O gas, and on the right-hand side, we have 4 moles of H2 gas. So this one will actually stay the same, since the moles of gas on both sides are equal. Okay, so now it wants to know, will the following equilibria shift left, right, or remain unchanged due to an increase in pressure? Okay, so the first one we have CO gas combining with gaseous water vapor to give us CO2 gas and H2 gas. Okay, so we're increasing the pressure. What will happen? So we have 2 moles of gas versus 2 moles of gas. Okay, so no change. Here we have 2 moles of CO gas giving us carbon solid and CO2 gas. So if we increase the pressure, which way will it shift? Okay, it of course shift towards our products. In other words, it'll shift right. Here we have N2O4 gas and 2 moles of NO2 gas. So 2 moles versus 1 mole. So we're increasing the pressure. So of course this would shift towards the reactants. In other words, to the left. Okay, this next one wants to know, it gives us an equilibrium reaction. It says predict which direction the equilibrium will shift, left, right, or no change, when each of the following changes are made. So we have N2O3 gas giving us, or is in equilibrium with, NO gas and NO2 gas. And they tell us delta H is plus 40.5 kilojoules per mole. So we have an endothermic reaction. So first it says adding more N2O3. So adding more reactant. So that shift right, left, or no change. So if we add reactant, we'll shift towards our products. So we'll shift to the right. Here we're adding more NO2. So here we're adding more product. So that will shift to the left. So remember, each of these is just a stressor we're applying. And you're asking yourself, how can the reaction, or how can the equilibrium shift to relieve that stress? So it says increasing the volume of the reaction flask. So now we need to look at the moles of gas. Okay, so that would shift towards the left. Oh, I'm sorry, to the right. So we've increased the volume. I was thinking pressure. So if we increase the volume, we'll shift toward the side with greater moles. So that would be to the right. What about lowering the temperature? Okay, so we have endothermic reaction. So does that make heat a reactant or a product? So if we lower the temperature, we're removing a reactant, so that means it would shift to the left. Okay, and I think we'll go ahead and stop there. There's a couple more questions at the end that you can go over on your own, but hopefully now you have a good idea of what you're doing. If you have any trouble, do let me know.